Hi everyone, today I'm looking at a question that a student has sent through saying that we're required to prove that 20C3 times 3C3 plus 20C4 times 4C3 plus and so on up to 20C20 times 20C3 is equal to 20 to the power of 17 times 20C3. Now the first point to note before I even dive into this is that I suppose one reason the student who sent this through was probably struggling is because the question has an error in it. The right hand side here, which says 20 to the power of 17 times 20C3, it should actually be 2 to the power of 17 times 20C3. And the way I spotted that error is, as I was thinking about this, I just couldn't work out how to show this was true. Like as I worked through the math, it kind of became clear that there's no way this could be true. And I opened up a spreadsheet and put the numbers in, and it showed that we were out by a factor of 10 to the power of 17, which kind of made it clear that this right-hand side was meant to be 2 to the 17, not 20 to the 17. So I asked the student who sent this through where the question came from, and they confirmed it came from almost like a mock trial paper put together by a coaching college. So hopefully they've noticed this error now and have sorted it out, because I got to say, as a student, there's nothing worse than wasting your time trying to answer a question that's got an error in it. I mean, there's no better way to waste your time than that. So in any case, I'll now work through this proof without the error, so with the right hand side being 2 to the 17 times 20C3, and let's take a look how we go about doing that. So here I've got what we're being required to show with the correct right-hand side. So I think the key here will just be to think about how we can simplify the left-hand side. And I think the first helpful thing to do is actually to put this left-hand side into sigma notation, which may sound a little counterintuitive at first, but I think the sigma notation will help us then make a link to the binomial expansion, which is going to help us here. So whilst for a lot of people sigma notation is probably more complex to deal with, actually here I think it helps us. So let's write this left-hand side as the sum from k is equal to, and here we've got to think about what our boundaries of the sum should be. I guess it makes sense to start from k is equal to 0. I think that's kind of a very common thing to do. But that means we're not going to be going up to, say, k is equal to 20, even though it's 20 sitting at the top of all of these 20Cs, 20C3, 20C4, and so on. Actually, because the difference between what's at the top of the combination and the bottom is 17, actually it makes more sense to make the sum go from k is equal to 0 to 17, and we have 20 c k plus 3, because we're starting at, if we've got k is equal to 0, it would be 0 plus 3 is 20c3, 1 plus 3 is 20c4, and so on. So we've got a k plus 3 here, all the way up to 17 plus 3 is 20c20, times, and then here it's 3c3, 4c3, and so on. So we start at k plus 3, so when k is equal to 0, we get 3c, and it's always a 3 down the bottom here. So it'll be 3c3, 4c3, and so on, up to 17 plus 3 is 20c3. So that's the sigma notation. Now, at this point, I think it's helpful to actually use our basic formula for a combination to write out each of these combinations in factorial notation and see if anything cancels and simplifies. So let's do that. So we'll get a sum from k is equal to 0 to 17. And maybe just over to the side, I'll note the rule I'm using, which is that NCR is equal to n factorial on r factorial n minus r factorial. That's one of the first rules you'll learn with combinations. So 20c k plus 3 would be 20 factorial on k plus 3 factorial times 20 minus k plus 3 factorial. And then that's times k plus 3 factorial on 3 factorial, k plus 3 minus 3 factorial. And the reason that's helpful is we can see right away these k plus 3 factorials cancel, and so we end up with the sum from k is equal to 0 to 17 of 20 factorial on 3 factorial times 20 minus k minus 3, which will give us 17 minus k factorial. And also we've got 3 minus 3 on a k factorial here as well. So that's what we've got. Now, what would be nice is if we could bring out of here a 20C3, because we know in the result we're looking for, there's a 20C3. We've kind of got a bit of it. We've got a 20 factorial and a 3 factorial. So we just need a 20 minus 3 factorial, and we'd have using this rule, 20C3 that we can bring out because there's no k. So the way we can get there is we'd like a 20 minus 3 factorial in the denominator. So let's put that there, 20 minus 3 factorial. But if we want to do that, we also have to put it in the numerator so that we haven't changed anything. So if I just write out this summation again, let's just put together the bits that are helpful together. So we'll have a 20 factorial on 3 factorial, 20 minus 3 factorial. So that has that bit, and that bit. And then we do times, and we'll put the rest together. So we'll have 20 minus 3 factorial on, maybe I'll just write this k factorial first, 17 minus k factorial. Now, as I mentioned, this here we know will be 20C3, and because there's not a k in that, we can bring it out the front of this summation. So we get 20C3 times the sum from k is equal to 0 to 17. And at this point, I think it's more helpful to write the 20 minus 3 as 17 factorial on k factorial, 17 minus k factorial. And again, making use of this basic rule, we can see that this is 17ck. So let's write that. So it's 20C3 times the sum from k is equal to 0 to 17 of 17ck. Now, at this point, we kind of know that we need to show that this summation here is equal to 2 to the power of 17, and we're done. And whenever you kind of see a summation with a combinatorial in there, something worth thinking about is the binomial expansion. So let's note that our binomial expansion in most generic terms says that x plus y to the n is equal to the sum from k is equal to 0 to n of nck x to the k, y to the n minus k. And sometimes you can flip around the order of the x and y and what the exponents are. But for our purpose, that order doesn't really matter, because what we're going to do is we're going to let x be equal to y be equal to 1. And the reason that's helpful is because we're going to end up with 1 plus 1 to the power of n, or in other words, 2 to the power of n, and we want 2 to the power of something, so this is really going to help us. So if we do that, we end up with 1 plus 1 to the n is equal to the sum from k is equal to 0 to n of nck, and then we have 1 to the k, 1 to the n minus k, but 1 to the anything is just 1. So it's actually just n to the k. So 2 to the n is the sum from k is equal to 0 of nck. So what that means is 2 to the power of 17 is equal to the sum from k is equal to 0 to 17 of 17ck. And that's exactly what we've got here. Sum from k is equal to 0 to 17 of 17ck. So that is 2 to the 17. So therefore, the left-hand side is equal to 20c3 times 2 to the 17. And even though the order is reversed, it doesn't matter because we're multiplying. So that is equal to the right-hand side as required.
Sonic boom!
All right, so that's how you can tackle that question. So obviously, first point is to, have the question not have an error in it. For any student seeing this question with 20 to the 17, they'll probably struggle forever because it's impossible to show. I suppose one of the benefits of having things like Microsoft Excel handy is when you've got questions that actually have numbers in it with combinatorials, you can actually go and throw it in Excel and just make sure that what you're dealing with is correct. Obviously, that's not an option in a real exam, but when you're studying and trying to work this stuff out, a tool like Excel can be really handy as a way to verify what you're doing and checking your work in a way. But once we start with the correct question, the answer essentially comes from doing a bit of simplifying, all focused around our basic rule around NCR, and then eventually making the link to the binomial expansion where we're dealing with a simple case of x and y being 1, and that gets us a 2 to the power. So I guess pretty straightforward in terms of the actual mechanics of what we have to do, but a little bit tricky in that you have to make a few links. First link being, take this summation and put it in sigma notation, because that's going to help us kind of make that direct link to how the binomial expansion is set up. I suppose it might not be as obvious that the binomial expansion will help us if we've just got it in this format here. So yeah, there you have it for that question. Hopefully that explanation makes sense and you've been able to follow along. And tick boom.